Hi guys, so in this lesson we're going to talk a little bit about how intermolecular forces have an impact on the behavior of substances, particularly in the liquid state. Think about this: in the gas state, particles are not interacting, so intermolecular forces really don't play a role in affecting behavior. However, in the liquid state, particles are constantly in contact with one another, and so the strength of those intermolecular forces is definitely going to make a difference. Let's start with surface tension. Okay, surface tension is the strength of attractions along the surface of a liquid that cause it to hold together at the surface. Uh, I bet you've done the penny demo where you drop water on top of a penny and see just how much water you can get to sit on top of a penny. And if you do it really slowly, you can get the water to kind of ball up like that and have a very rounded surface, okay? That's defying gravity. Gravity should pull the liquid off the penny, but it doesn't, and the reason is the surface tension of the liquid. Water does this very well because water has very strong intermolecular forces. Other liquids with weaker intermolecular forces would not be able to accomplish this. Boiling point. Boiling point, as you know, is the temperature at which a liquid reaches a maximum liquid temperature and converts from a liquid to a gas. Okay, the stronger the intermolecular forces, the higher the boiling point of the liquid would be predicted to be. If the forces are stronger, the particles are holding together with greater strength, and therefore more energy is needed to overcome those intermolecular forces. Vapor pressure is a little bit trickier to explain, but not really. Vapor pressure is the pressure created by gas evaporating from a surface of a liquid. So if I were to put some water in a closed container, some of that water would evaporate in that container and create a vapor pressure. Ultimately, when the vapor area is full, I would have an equal number of particles converting from liquid to gas and back again from gas to liquid once we reach maximum vapor pressure. The higher the vapor pressure is, the more particles are in the gas state. How is that going to be related to intermolecular forces? If you think about it, stronger forces, less evaporation, lower vapor pressure. So you may want to just take a moment and enter in your notebook right now how the boiling point, surface tension, and vapor pressure would be impacted by strength of intermolecular force. And pause here before you go to the next slide. We're going to be talking about water particularly here when we discuss capillary action. Capillary action is an interesting behavior of water in a tube. If you take a tube and set it into a dish of liquid water, there is some tendency of the water to climb up the tube and cling to the walls of the glass tube. That's called capillary action. And that is caused by adhesive forces between the water and the glass surface of the tube. There are cohesive forces that exist between the water molecules in the liquid. And the degree to which the water climbs up the tube has to do with a balance between the cohesive forces within the water and the adhesive forces between the water and the glass. I'm going to set up a demo for you, I hope, when I get back in the lab, and show you how the diameter of this tube impacts the height that the water climbs up the tube itself. Okay. This is an example of a phase diagram. Okay, and what you see in a phase diagram is essentially a plot of the borders between the three states of matter as a function of pressure and temperature. There are three zones to this diagram. The zone that exists at highest pressure and lowest temperatures is where a solid would exist. The zone where the temperatures are highest and pressures are lowest is the gas zone, and the intermediate zone is the liquid zone. Okay? And this just shows you the impact that pressure and temperature have on the state of matter. You can also see in this diagram the labeled transitions that we saw in the previous slide lesson. So just kind of familiarize yourself with that a little bit. I need to take a few more minutes to talk about boiling point, okay? Because actually the definition that I gave you 2 screens ago is not really the accurate definition of boiling point. So let's clarify this and see how this graph can help us understand boiling temperature for a variety of liquids. First, the definition of boiling point. It's probably a good idea that you write this down so that it is very emphatic that you know this particular definition, because boiling point is not always the same number. It has a total dependence on the external atmospheric pressure above the liquid. Let's look at the curve first here for water, because that's the curve with which you are the most familiar. You remember when we were studying gases, we talked about collecting a gas over water, and we said that there was some component in the gas sample that was collected of pressure caused by water evaporating into the gas sample. You notice that pressure is very low at low temperatures, and it increases as the temperature of the liquid increases. At some point, okay, the vapor pressure of the liquid, the pressure inside the bubbles of the liquid that form when it boils, can be equal to the atmospheric pressure. Now, in a normal place at sea level, at standard atmospheric pressure, that would be a pressure of 760 torr and corresponds to a boiling temperature of 100 degrees. However, if the external atmospheric pressure were to change, let's say you climb to a mountaintop where the pressure is less, then in fact what would happen is the boiling point of the water would decrease somewhat, because the pressure inside the liquid bubbles as the liquid boils would not have to reach 760, might only need to reach 700. Okay? If external atmospheric pressure were higher, then the boiling point of water would increase. Okay? So boiling point is pressure dependent for these liquids. Now, I've kind of glommed up this graph here, but let's take a look at the other liquids. We have got ethanol, which is also a polar liquid, though not quite as polar as water. And we have diethyl ether, which is only slightly polar. I'll show you some structures in class. And you can see here that the boiling points of these liquids are lower because the intermolecular forces are easier to overcome. Ethylene glycol down here is a molecule with even stronger intermolecular forces than water. And in this case, the boiling point of the liquid, well, who knows where that would be? Okay, it would be way up here somewhere at a very high temperature. Okay? So we have talked about what boiling point is. You've got that definition from the previous screen. Check that off. And how is it related to IMFs? If we have stronger intermolecular forces, boiling point would be higher. If we have weaker intermolecular forces, boiling point would be lower. Okay? So here's a table of a variety of data. We have some formulas for some compounds, some names, molar masses, and boiling points. Okay? So I'd like you to pause the video and take a look at these data for a few minutes. All right, and just kind of get a peek at changes in molar mass, changes in boiling point, and then I'm going to ask you a couple of questions and have you block some things out in your notebook based on these data. So go ahead and pause for a moment or two. So for your first question, I'd like you to take a look at the boiling points of methane, ethane, propane, and butane and explain that boiling point trend related to IMFs. Now here I'd actually like you to literally shut the video off, pause, shut it off, pause it, and write a 1 or 2 sentence explanation, your explanation for the observed trend in boiling points. For the second question, I would like you to compare the boiling points of methane and methanol and explain that difference due to IMFs as well. 1 or 2 sentences is all it takes to justify this trend. Pause the video again. The final question here is to compare the boiling points of ethanol and propanol and justify the difference based on specifics of intermolecular forces. Okay, now if you haven't answered these 3 questions, please pause, because I'm about to answer them, and I would like you to have a shot to try before I answer them. For the first question, you notice that all of these compounds, methane, ethane, propane, and butane, are nonpolar. They are all carbon-hydrogen compounds, and so they would all be experiencing London dispersion forces as their intermolecular forces. However, as you go from CH4 to C2H6 to C3H8, etc., the molar mass is increasing, the particle is getting larger, and the electron population is increasing as well. And increasing particle size and number of electrons leads to greater polarizability. So the IMFs, the London dispersion forces, in butane are significantly stronger than those of propane, which is stronger than ethane, which is stronger than methane. For question number 2, methane is a nonpolar substance with London dispersion forces acting between particles, and methanol has the OH group sitting on the end of it that allows it to form hydrogen bonds with other compounds, or with other molecules of itself. And so the reason the boiling point of methanol is so much higher than the boiling point of methane is due to the presence of hydrogen bonding between methanol molecules that does not exist in methane molecules. Question number 3, ethanol and propanol. Both of these particles have the OH group on the end, okay? However, the propanol molecule is a larger, longer chain of carbons, and the bigger molecular size, in addition to the larger number of electrons, makes it more polarizable. So even though they both have some hydrogen bonding, the polarizability of propanol is greater and leads to stronger intermolecular forces. Please be sure to bring these notes and ask questions in class or CCL if we need to clarify. And we will be talking about these topics in class this week. Thanks, guys.